Hello, everyone. Today we are doing section 12.5, and this is our last section we cover in this class. The section is called the Mathematic induction. So we are going to learn about a special kind of proof in math, which is called mathematic induction. And usually mathematic induction proves statements about natural numbers. Natural numbers are numbers like 1, 2, 3, 4, 5, and so on. Before I talk about the method, I want to kind of visualize it a little bit. So imagine that we have a very, very long road, and it starts at the Earth and goes to Mars and even further away, like I did on my drawing. And there are cars all like bumper to bumper driving on this road. And imagine that on the Earth we have a light signal, traffic signal, which shows stop. So red signal light. What is going to happen? Well, everyone kind of knows that they have to stop on red. So the first car stops. I'm going to rail stops. What is going to do the second car? The second car is going to probably see the signal and stop too, right? So, well, the third car probably won't see the signal already, but he sees that the previous car stopped and he's going to stop, right? He doesn't want to crash. And you understand that all the cars are gonna just like see that the previous car stops, that they are going to stop. And what is going to happen to this car nearby the Mars, which are far, far away, right? What is going to happen? Well, probably this car is going to stop because it's going to see that the previous car stopped, right? Sorry, instead of stop, red spot. Stop. And this car, that's the next one, is going to stop because it's going to see that this one is going to stop, right? And actually, all cars in this long, long line, maybe which goes to infinity, I'm going to put infinity sign over here. All cars are going to stop just because, well, as soon as they see that the car in front of them stop, next one is going to stop and next one is going to stop. And it's going to look like a chain reaction. Actually, mathematical induction is using a similar pattern to prove statements. Usually how it works. Well, if we have a certain statement about natural numbers, I'm going to just write down one for example statement. For example, the statement is 2 plus 4 plus 6 plus 8. You see, these are like even numbers, and plus 10 and plus 2n. If you add up n even numbers, the result is going to be equal n plus 1. This is a typical statement about natural numbers. Here n is a natural number. So how do we prove statement like this? First, we are going to make sure that the first car stops. Well, that's like a correct statement for us. So that a statement is working for n equals 1. For example, in this case, if you set up n equals 1, you are going to have just one number here. It's 2, right? N equals 1 is going to be 1 multiplied by 1 plus 1, which is going to be also 2, right? So the first car stops. Second, we are going to make sure that cars who are going to see that the car before them stop are going to stop too. For example, if this one stops, then the next one is supposed to stop here. We're going to call it a step of induction. Step of induction. Well, do we know that this one stops? Well, not for sure, actually, right? But we do know that the first one stops, and we know that the second is going to stop just because there is no way for second to go, right? And the third is going to stop. And if we prove the step of induction that next one stops if previous one stops, then we can kind of pull all these cars up to infinity. So same with numbers, right? If we make an assumption that car number k stops and show that from this follows that this one is going to stop. Well, from my picture, it's obvious, right? This one does not have any place to move, but like for numbers, who knows how they behave. If we make an assumption that this one stops, and from this assumption can prove that this one is going to stop, then we can pull all these cars up to infinity. And that's how it's going to work on numbers too. So I'm going to show the proof for this example, and then I'm going to consider 2 more examples. I know that mathematical induction is not that easy to believe from the first sight, but if you practice, you will like this method as I liked it too. So I'm going to start working on this example. So first I'm going to check that for n equals 1, it is true. Well, we kind of already check it, but just make sure. N equals 1 means that there's one number here, right? And n equals 1 here, it's 1, 1 plus 1. Well, obviously this side is 2, and that's true. Now, that's going to be number 1. Number 2, I'm going to, by the way, label it as a proof. Number 2, assume that it is true for n equals k, like over here the car stops. Well, what does it mean? Well, you just copy the statement and write down that just like instead of n, put k here. So it's 2 plus 4, and I'm going to put lots of dots, and 2k equals, and put k here instead of n, and put k here instead of n. It's k plus 1. So we don't know that this is true, but we are kind of assuming that it's true. Maybe it's not true, but if this car stops, next one is going to stop definitely, right? So we are going to prove it actually. Need to prove. And this is going to be actually step of induction. It is true. It is true for n equals k plus 1. How it's going to look for k plus 1? It's going to look like this. 2 plus 4 plus k. And the next one is going to be 2k plus 1. Right? Next term is added. And here instead of k, I'm going to put k plus 1. And here instead of k, I'm going to put k plus 1. Okay, so that's what we are proving. What we can use in this proof? We can use general math logic. For example, we can use that like 2 equals 2, or like, I don't know, 1 less than 2. We also can use our assumption. So I'm going to put specifically here, we can use our assumption. Because temporary, our assumption is true, and our assumption is over here. What I'm going to do, guys, I'm going to work on my right side a little bit and just copy my left side for a while, like without any change. So I'm going to copy 2 here, 4 here, plus 2k, plus 2k plus 1 equals here. What I'm going to do, guys, I'm going to simplify and write down that this is k plus 1. And over here, it's k plus 1 plus 1. It's k plus 2, actually. And I'm going to open this parenthesis. I'm going to multiply k by this parenthesis and 2 by this parenthesis. I'm not going to total open it. I'm just going to write down k plus 1 by k plus k plus 1 by 2, partial open parenthesis. What I do know already, let me choose a different color. I do know that this part, 2 plus 4 plus 2k, equals to k plus 1, which is this one, right? So this one already equal, and I'm going to write down equal by assumption. I don't know if assumption is true or not, but at least like temporarily it's true. Okay, what I have left? I have this one, 2k plus 1, and I have this one, which is actually also 2k plus 1, because 2 is same, k plus 1 is same. So these two things are just equal without any assumption. They are just literally equal. They are just equal. So our statement is true, just because this last term here and last term here are equal, because they are just the same terms, and the first term here and the first n terms here, or k terms here, are equal by assumption. So we're going to make a statement that it's true, and kind of we did a step of induction. So I'm going to write down we did a step of induction. Now, what we are going to do? we can show that everything is going to be true for all n. You don't need to do it every time. Actually, the method is well known, and if you do this step 1 and step 2, that's going to be enough to finish the proof. But I want to continue it once to show how logic works after this point. Now, we do know that if it's true for n equals k, it's going to be true for n equals k plus 1. Now we are going to set n equals k equals 1. And we do know that for 1, it's true already. We just checked it. True. Right? Well, from this one, because we proved it in step number 1, I'm going to write down, we checked it. What we can do? We can make a statement that, like, by number 2, that's now in our assumption, but it's not really assumption, it's actually truth. K plus 1 is going to work. So I'm going to write down then k plus 1, which is going to, in our case, 2, is true 2. And k plus 1, which is 2 plus 1, which is 3, is true 2, and so on. So we basically can pull all natural numbers using this step of induction, and not assumption already. This is not assumption, right? The first statement is not assumption. That's a true statement. We just checked it, that 2 equals 2. So we kind of conclude the proof at this point. Okay, I'm going to consider 2 more examples. Not all examples are going to be like just proving of the formula. Some examples are going to be proving inequalities or some logical statements about natural numbers. So I'm going to move to the next page and prove another example. Example 2. Somebody is asking me to prove that 4n is less than 2 to the power of n for all n greater or equal than 5. This is example 3 from your book. How I'm going to prove it? Well, first I'm going to check if it's true for n equals 5, right? We start with n equals 5 because it's just like that problem is telling us this. So n equals 5. So what do we have? We have 2 by 5. Oh, sorry, not 2, 4 by 5. Why did I write down 2? We have 4 by 5, supposed to be less than 2 to the power of 5. Is a true statement. Well, what is 4 by 5? 4 by 5 is 20, and 2 to the power of 5, it's actually 32. So true statement. Okay, very good. So we just proved that it's going to work for step number 1. So the first car stops. Now, assumption. Assume that it is true for n equals k. How is it going to look for n equals k? Well, for k less than 2 to the power of k, right? My k doesn't look very nice here. I'm going to write it out again. Hey, come on, for k. Just like somebody's going to watch what I'm writing down in notes, and it's going to be hard to understand. Okay, so this is assumption. Need to prove. That is going to work for n equals k plus 1. Sorry, I'm getting lots of different little tiny dots while I'm touching a whiteboard. So how it's going to look for k plus 1? Well, for k plus 1 here, supposed to be less than 2 to the power of k plus 1 here. I'm going to be very simple proof. What I'm going to do, guys, I'm going to do little modifications. Again, what we can use here, I'm going to write it down. We can use our assumption. Actually, we're supposed to use our assumption somewhere. Otherwise, why do we need the assumption if we're not planning to use it anywhere? So how are we going to use it? Let me change the color, and I'm not gonna do anything to like my right. Well, I'm going to open parentheses on my right side. So I'm going to write down 4k plus 4. Supposed to be less. I don't know if it's true or not, but supposed to be less. What I'm going to do over here, remember guys, when we add the number to the power, we actually mean multiplication by the number with same base. So actually, when we write down the power k plus 1, we actually mean multiplication 2 to the power of k by 2 to the power of 1. Because base is same, we can add the powers and get k plus 1. Now, 2 to the power of 1 is, of course, just 2, right? So we have 2. Sorry, my 2 doesn't look really very. We have 2k just by 2, right? What is something multiplied by 2? Well, what is 2 apples? That's apple plus apple, right? So I'm going to write down 2k plus 2k. Well, if you add 2k plus 2k, you're going to get double 2k, right? Now, guys, I'm going to start using my assumption. I know that 4k is less than 2k. I'm going to put a sign less. One. How do I know this? By assumption. By assumption. What do I have left? I have 4 on this side. Let me change the colors so you kind of will understand like what I'm doing. I have 4 on this side and 2k on this side. Are they going to kind of make a true statement too? Well, let's consider how 4 is related to 2 to the power of k. Well, you know that if k equals 1, that's not true, like not true statement. 4 is greater, right? But when k is, what's supposed to be k to make it actually working? Well, for example, if k equals 2, we have 2 to the power of 2, which is 4. It's not less than 4. But if k equals 3, it's going to be greater, right? K equals 3 here, it's 8. K equals 4 is going to give us 16. And all the numbers starting with k equals 3 are going to be greater than 4. Well, how about our k? Is it greater than 3? Actually, k here is not only greater than 3, it's going to be greater than 5. So we're going to write down k greater or equal than 5. So it's true because of this, because of the condition, right? So now I'm going to unify these two statements. I'm going to write them separately and show that I add them. So 4k is less than 2 to the power of k, assumption. And 4 is less than 2 to the power of k. K greater or equal than 5. Well, that's just by the condition of the problem. Actually, it's going to work even for smaller case. So if you add these two inequalities, you're going to get 4k plus 4 is less than 2k plus 2k, right? Remember that this side is 2 by 2k or 2k plus 1. And this side is 4k plus 1. If you consider this part and this part, that's exactly what we are proving, right? 4k plus 1 is less than 2 to the power of k plus 1. So we proved a step of induction. Do you need to, after that, explain that now we can pull all the natural numbers? No, that's actually included in the method, so everyone understands that. If you prove the step of induction, then, and you have the first statement true, you can pull all natural numbers. So you don't need to repeat it every time. Okay? Okay, very good. That was example number 2. And the last example, example number 3, slightly different from first two examples because they were formulas. And last example is going to be something like a logical statement. Let me move to the next page. Give me a second. So my next example, example number 3. We need to prove that n squared plus n is divisible by 2 for all natural n. So I'm going to kind of write down what means for all natural n. N is greater or equal than 1. Okay. And let me erase again my little tiny dots, which I don't need, and start proving it. So I'm going to first say what is divisible by 2. What is divisible by 2? 2 is divisible by 2, 4 is divisible by 2, 6 is divisible by 2, right? You can divide number by 2 if it's even number, or if you can represent number as 2p. 2p is like 2 multiplied, and p here is a natural number, natural. So for example, 2 multiplied by 3 equals 6, divisible by 2. Divisible by 2. So this is just like definition, what we consider divisible by 2, because like when saying divisible by 2, how do you understand this? That's not a formula, right? So actually we can represent it as 2 multiplied by some natural number p or q or whatever, like natural number. Natural number is number like 1, 2, 3, or 4, 5, 6, and so on. I'm going to start my proof. So I'm going to write down proof. Number 1, I'm going to check if it works for n equals 1. For n equals 1, what we have? 1 squared plus 1 equals what? It equals 2. Is 2 divisible by 2? I'm going to write down divisible by 2. So true. It's true. Sorry, supposed to be one more e here. Let me erase this. True. I wrote it badly. True. Now, assumption. Assume that it is true for n equals k. How it looks? Well, for n equals k, it's going to look like that. Sorry. Where's my razor? Razor. That k squared plus k divisible by 2, right? That's true. Well, we are going to write down that it equals to 2p, p natural. So we are trying to write down as mathematical formula the fact that it's divisible by 2. I'm going to put it in parentheses. Divisible by 2. Okay. Need to prove that it's true for n equals k plus 1. How's going to look for k plus 1? That's going to be k plus 1 instead of k, right? Squared plus k plus 1 instead of k. And it's supposed to be equal to q. Well, it's still supposed to be divisible by 2, right? But number which is over here is not necessarily supposed to be the same number here, right? It's just supposed to be like 2 multiplied by some natural number. So I'm choosing a different number for it. Okay, I'm going to write down q natural. Maybe they are going to be related, but for now, it's not important. How are we going to do it? Are we going to prove it? I'm going to consider my right side and open parentheses. I'm going to write down that k plus 1 squared plus k plus 1 equals k squared plus 2k, right? The formula a squared plus 2ab plus b squared plus k, copying the last two terms. Now, guys, what I'm going to do, I'm going to unify k squared and k because they sit in our assumption. So I'm going to write down k squared plus k. And I'm going to unify the rest. The rest is this, and this. That's 2k, 1, and 1. So I'm going to write down 2k, and 1, of course, is just 2. Now, I do know that k squared plus k equals 2p. That's my assumption. So I'm going to write down 2p by assumption. Now, here I'm going to take 2 outside of parentheses and write down k plus 1, 2 from here and 2 from here. No, I just used my assumption. I'm going to take this 2 and this 2 outside of these two terms. I'm going to write down 2 here. Left over from the first term is p, and the second term is k plus 1. So guys, it does not look like I proved anything, but if you compare my statement over here to what I'm trying to prove, you can say, okay, if we set up this number as q, if we label it or call it as q, we actually did not specify what's supposed to be q, it's just a natural number. It's going to be exactly equal, right? It's going to be 2 multiplied by some natural number. How do we know that q is a natural number? Well, we know that p is natural number. K is natural just because k is like one of the numbers which are coming in a series, like 1, 2, 3, 4, 5. And 1 is natural number just because it's the first natural number. So all of them are natural numbers. So q is a natural number too. And we proved that it equals to 2q. And we even found what is q. Q is going to be p plus k plus 1. Here we did not know this, but after we did the proof, we already know. So we did the step of induction. We did show that number k plus 1 squared plus k plus 1 is equal to 2 multiplied by some natural number. So if you take this number and divide by 2, you are going to get q, which is natural number, and 2 is going to disappear, so it's divisible by 2. I'm going to write down divisible by 2. Okay, that was our last example. Well, my suggestion, guys, if you do like 3-4 examples on your own, try to do different examples. Eventually, you will like this method. Method is very cool and nice. Okay, that's all for this lecture.